Ever feel like you're drowning in information trying to pull out what's actually useful? Well, it turns out even powerful AI, like the large language models we hear so much about, kind of face a similar problem when they need to think things through.
It's a real challenge.
So today, we're doing a deep dive into something called Deep Think with Confidence, or DeepConf for short. It's a pretty interesting new method designed to help these LLMs reason more effectively.
That's right. The goal is to help them cut through the noise, essentially, and get to better answers faster.
So maybe set the stage for us a bit. How do LLMs typically reason through complex problems now?
Well, a key technique involves trying out multiple lines of thought simultaneously, different ways to get to an answer. Think of it as parallel thinking.
Okay, parallel thinking. Makes sense, like brainstorming different solutions.
It does boost accuracy, often quite significantly. But there's a catch.
Always a catch. What is it?
It's the cost. Generating all those different thoughts uses up a lot of computational power. We're talking huge amounts of text, millions of tokens sometimes.
And I guess more thinking isn't always better thinking.
Sometimes, yes. You can hit diminishing returns, where generating even more pathways doesn't improve the final answer and might even make it worse.
So what was the core problem DeepConf set out to solve then? If parallel thinking is good, but costly.
The issue was that older methods tended to treat all these thinking paths, these generated reasoning traces, as equally valid. And crucially, they usually had to wait until the whole thought process was finished before figuring out if it was any good.
Right, so you couldn't tell early on if a path was heading in the wrong direction.
Correct. You'd miss those early warning signs.
Which brings us to DeepConf. It seems like its big idea is about using the model's own feelings, its confidence.
Kind of, yeah. It taps into the model's internal confidence signals. It uses these signals to filter out the low-quality reasoning paths as they're being generated, or sometimes after the fact.
And the promise is better accuracy with less work.
Yeah, essentially, yes. Boost accuracy, cut down the computational load. It's designed to be a simpler yet powerful solution.
Okay, let's unpack that. You mentioned parallel thinking before. Can you give us an example, maybe with like a math problem?
Sure. Imagine an LLM solving, say, a complex algebra problem. It might generate dozens, even hundreds, of different step-by-step solutions. That's the parallel thinking.
And how does it usually pick the right answer from all those attempts?
A common method is called self-consistency with majority voting. The model generates many reasoning paths, gets an answer from each, and then the final answer is whatever the majority of paths agreed on.
Like taking a poll of its own thoughts.
And it worked pretty well for improving accuracy.
But back to the cost issue. You said generating hundreds of traces is expensive. How expensive are we talking?
Very. The research mentions a case, the AIME 2025 benchmark, where getting accuracy up from around 68% to 82% needed over 500 extra reasoning traces.
Wow.
And those extra traces added up to something like 100 million extra tokens. That's a massive computational cost.
And you also mentioned diminishing returns, where more isn't always better.
Right. Pouring more compute, generating more traces doesn't guarantee a better result. Sometimes accuracy just plateaus or even dips a bit, probably because you're adding more of a noise, more incorrect paths into that final vote.
So before DeepConf, attempts to judge the quality of these paths, they weren't quite cutting it.
Efforts were made using global confidence measures, sort of an overall score for an entire reasoning trace.
Like a final grade for the whole thought process.
Yeah, but they often missed crucial mistakes made halfway through. And again, they usually required the entire thought to be completed first. Lots of wasted effort on paths that were doomed from the start.
Okay, so DeepConf comes in with this idea of listening to the model's confidence along the way. How exactly does it do that? What signals is it looking for?
It focuses on more local signals, not just that overall global score. It's like checking the quality of different steps on an assembly line, not just the final product.
Makes sense.
And the key thing is, it uses signals the model already produces internally. No extra training needed, which is a big plus. I can just plug into existing systems.
So what are these local signals?
There are a few. The most basic is token confidence. For every single word or token the model generates, it has a certain confidence level. High confidence means it's pretty sure about that specific word choice.
Okay, confidence word by word.
Then there's group confidence. This smooths things out by averaging the token confidence over a recent window of tokens, say the last 1,000 or so. It gives a better sense of confidence over a whole step or sentence, not just one word.
So it catches slightly bigger wobbles in the thinking.
Exactly. And then it gets really interesting when it looks at low confidence points.
Ah, looking for the weak spots.
Right. One metric is the bottom 10% group confidence. It averages the confidence scores from the 10% least confident parts of the reasoning trace.
Why focus on the lowest parts?
Because really low confidence often signals a major problem. You might see the model internally generating tokens like wait or think again in these low confidence areas. It's basically telling us it's unsure.
I see. Like the model itself is hesitating.
Precisely. There's also the lowest group confidence, which is even more focused. It just takes the confidence score of the single least confident group in the entire trace. This one turns out to be really useful for stopping bad traces early.
And you mentioned one more.
Yes, tail confidence. This looks specifically at the confidence in the final part of the reasoning, like the last couple thousand tokens. This is important because the final steps are often critical for getting the answer right, especially in math or logic problems.
So instead of one overall grade, DeepConf uses these more targeted checks, word level, group level, looking at the lowest points and checking the ending.
That's the idea. And the research shows these local metrics, especially the ones focusing on low confidence like bottom 10% and tail confidence, are much better at telling good reasoning paths from bad ones compared to just averaging confidence over the whole thing.
Okay, that makes sense. So how does DeepConf use these signals in practice? You mentioned offline and online.
Correct. It can be applied in two main ways. Offline thinking is when the LLM has already generated all its reasoning traces. DeepConf then helps refine how we use those completed traces.
So improving that majority voting thing we talked about earlier.
Yes, in a couple of ways. First, confidence-weighted majority voting. Instead of each trace getting an equal vote for the final answer, each trace's vote is weighted by its DeepConf confidence score. High confidence paths get a bigger say.
So more confident thoughts count more. Seems logical.
And second, confidence filtering. Before even doing the weighted vote, DeepConf can filter out the least confident traces altogether. Maybe it only keeps the top 90% most confident traces, or even just the top 10% for a more aggressive approach.
What's the effect of that filtering?
Well, aggressive filtering, like keeping only the top 10%, can really boost accuracy. The paper mentions getting a GPT model up to nearly 99.9% accuracy on that AIME benchmark using this method.
Wow, that's a big jump from the baseline.
It is, but there's a small risk. Sometimes the model might be very confident, but still wrong. So aggressive filtering can occasionally hurt accuracy if it throws out diversity and focuses too much on a confidently wrong answer.
Ah, so there's a trade-off.
Yes. Using a more conservative filter, like keeping the top 90%, is often safer. It still provides benefits, but reduces the risk of that overconfidence issue.
Okay, that covers offline. What about online thinking? You said that's more dynamic.
Right. Online thinking is where DeepConf intervenes during the generation process. This is really valuable when you need answers quickly or want to save computational resources in real time.
How does it intervene?
It mainly uses that lowest group confidence metric we talked about. As the model generates a reasoning trace, DeepConf monitors this lowest confidence score in real time.
And if it drops too low?
If the confidence dips below a preset threshold, DeepConf just tells the model to stop generating that particular trace. It cuts it off early.
Because it's likely heading down a bad path anyway.
Precisely. Saves compute by not finishing unpromising lines of thought.
But how does it know where to set that threshold? How does it decide what's too low?
It uses a two-part strategy. First, an offline warm-up. Before starting on the actual problem, it generates a small number of initial traces, maybe just 16 or so.
Okay.
It analyzes the confidence scores from those warm-up traces to establish a reasonable starting threshold for the real task. It calibrates itself, essentially.
I see. And the second part?
Adaptive sampling. DeepConf watches how much agreement or consensus there is among the answers from the traces it has completed so far. If the answers start converging strongly, say 95% of the paths agree on an answer, it might decide to stop generating new traces altogether, even if it hasn't reached its full budget.
So it stops early if it's already pretty sure it has the right answer.
You got it. It adapts based on the emerging consensus. Both the early stopping of bad traces and the adaptive sampling of overall traces lead to significant efficiency gains.
And the results bear this out. How much does it actually save?
The numbers are pretty compelling. On benchmarks like AIME 2025, using online DeepConf, they saw token reductions of up to almost 85% for some models.
85%. That's huge, while keeping accuracy high.
Yes, generally maintaining or sometimes even slightly improving accuracy compared to the standard methods, especially when using the more conservative filtering approaches. The aggressive filtering saves the most tokens, but again carries that small risk we discussed.
So, pulling this all together, what's the main takeaway from DeepConf?
I think it really shows that we can make LLMs reason much more efficiently and effectively by intelligently using signals they already produce. It's about smarter utilization at test time, rather than just throwing more computation at the problem.
It's not just about thinking more, but thinking better.
Right. And crucially, it works across different model sizes and doesn't require costly retraining. It's a practical enhancement.
So, this feels like a step towards more scalable and reliable AI reasoning.
Definitely. Understanding and leveraging these internal model signals seems critical for deploying these powerful models effectively in the real world.
And for you, the person using these tools, this kind of research, points towards LLMs becoming hopefully more consistently reliable and efficient assistants.
Although it does leave us with an interesting point to ponder related to that confidently wrong issue.
Ah, yes, when the model is sure but incorrect.
Right. While DeepConf helps, it doesn't completely solve the problem of models sometimes having high confidence and faulty reasoning. How can we better detect and handle those specific cases? That seems like a key challenge for future work as these systems continue to improve.